Despite existing on a small planet in a tiny corner of the cosmos, astronomers know exactly how much visible matter the entire universe should contain. The problem is that for decades, 40% of it has been missing. And I'm not just talking about the ever mysterious dark matter and dark energy. Galaxy clusters don't seem to have as much visible mass as our models say should be there. Entire galaxies seem to have lost huge reservoirs of the material they were born with. Even the space between galaxies, enormous cosmic deserts, are emptier than our best theories predict. This missing mass has to be out there. That, or all our models of cosmology, are wrong. But every time we've looked, we've found nothing. And believe me, we've tried. We've used our most powerful telescopes, deepest surveys, and most sensitive detectors in the search. The missing mass just remains invisible, slipping past our instruments like a ghost. That is, until now. For the first time in history, we may have finally found where the missing mass of all the universe has been hiding, and it's in plain sight. Astronomers have captured images of vast gaseous filaments that stretch 23 million light-years between galaxy clusters. It may just be one filament, but finding it has huge ramifications. Is this the very first detailed image of the cosmic web? As scientists now hunt for more, this discovery has the power to determine whether our cosmological models are correct. I'm Alex McColgan, and you're watching Astrum. Join me as we reveal how astronomers have snatched a glimpse of the near-invisible network that underpins the cosmos, finally revealing the hiding place for our universe's missing visible matter. And with it, let's start unraveling the truth behind our cosmic evolution. When we measure all of the gas, dust, planets, stars, and galaxies, everything we can see in the whole universe, using everything from infrared to visible light and beyond to gamma rays, it adds up to a colossal amount. More than 100 sextillion kilograms. That's 10 with 53 zeros after it. But really, this only accounts for a small fraction of the total matter that scientists predict to exist. In fact, this visible ordinary matter is thought to make up just 5% of the universe. The rest is stuff we don't completely understand. Dark matter is believed to account for 27%, and dark energy 68%. Despite their names, dark energy isn't related to dark matter. What they have in common is that we can't detect or see them. Dark energy is thought to be a seemingly invisible type of energy, causing the universe's expansion to accelerate over time. And dark matter is a type of matter that has mass, but is invisible to us, as it doesn't absorb, reflect, or emit any light. I've talked about dark energy in previous videos, and that is truly its own mystery. You can explore those if you're interested to find out more about the topic. But for this video, I'll just focus on the matter at hand. So, 95% of our universe is likely not made of visible, ordinary matter. And of the 5% that is technically visible matter, also known as baryonic matter, about 40% has been missing since the Big Bang 13.8 billion years ago. Now, I know what you're thinking. How do we know it's missing if we've never seen it? We certainly weren't around back then. Thankfully, the early universe itself left us the answer. Measurements of the cosmic microwave background have allowed cosmologists to calculate exactly how much baryonic and non-baryonic matter was created as a result of the Big Bang, to an accuracy level of better than a few percent. That gives us a precise budget for how many atoms should be in the universe today. But just because it's made of stuff that's visible to us doesn't mean it's easy to see. When astronomers go out and count up all the stars, gas, dust, and plasma we can see, with the help of models and simulations, we only find about 60% of what should be there. The rest has to exist for early universe physics to make sense, but unless we can find it, we can't prove that our models are right. Maybe we've got it all wrong. Thankfully, scientists haven't been that quick to give up, and instead turn their attention to working out where the missing mass may be lurking. And they came up with an intriguing hypothesis. Missing baryonic matter is not the only missing mass, and perhaps they're hiding together. Finding out that 40% of all baryonic mass is missing must have been seriously annoying for astronomers. Understanding the universe is much harder with such a fundamental gap in our knowledge. So why not fill those gaps? This is easier said than done when you're on the hunt for missing matter, but if you're trying to learn more about other subjects in maths, science, and computing, then Brilliant, the sponsor of today's video, is the tool for you. I really like Brilliant's interactive approach to filling in knowledge gaps. Their online platform gives you interactive challenges to try, because most gaps are easiest to fill through doing rather than just reading or memorization. And Brilliant's learning is personalized. It starts you on a level of learning that's right for you and helps you advance at your ideal pace. No need to find the matter that you've already located. I really like their course on scientific thinking, as it cemented for me just how momentum transfers in colliding objects, useful in space and at the pool table. So don't let Brilliant be among the 40% of matter in the universe you haven't seen. Scan my QR code or click my link in the description below to learn for free for 30 days on Brilliant. Astrum viewers who do so will also get 20% off an annual premium subscription, giving you unlimited daily access to all Brilliant has to offer. And now, back to our fascinating discovery. Nearly a century ago, Swiss-born astronomer Fritz Zwicky noticed that galaxies in the Coma cluster move too quickly for the amount of gravity that would be created by their visible matter alone, yes, including the missing stuff. Instead, he thought another form of mass must be there, and in 1933, Zwicky dubbed this missing substance Dunkle Materie, the German for dark matter. In the 1970s, American astronomer Vera Rubin had a similar experience. She was observing spiral galaxies and wondered how stars on the outer edge of the spiral galaxies were able to move so quickly without flying off into space. Again, some unknown mass must have been pulling them back in, and she concluded the same as Zwicky. There must be dark matter holding them together. This new type of stuff interacts with its ordinary baryonic counterpart through gravity, but it doesn't interact with the electromagnetic spectrum, meaning that it doesn't absorb, reflect, or emit any light. This makes dark matter extremely difficult to find, and seemingly impossible to observe, at least directly. Yet it influences the cosmos on a galactic scale. It may even be helping to conceal our missing baryonic matter. Since the 1980s, early observations of galaxy distribution have revealed a cosmic pattern, a web, like a backbone across the universe. This skeleton-like structure has become known as the cosmic web. It's thought to have formed as a result of slight density fluctuations in the early universe, which can be seen in the cosmic microwave background, or CMB, a fingerprint of our universe's ancient microwave radiation from about 380,000 years after the Big Bang. These tiny fluctuations in density laid out a blueprint for where matter would collect over space and time. Where there were higher densities, more mass would be drawn in, until this great structure was formed. We already know that CMB simulations using supercomputers estimate that dark matter accounts for 5 times more of the universe than ordinary matter, so it's perhaps no surprise that the cosmic web is thought to contain primarily dark matter. Permeating every corner of our universe, it's made of filaments stretching tens to hundreds of millions of light years across the universe. Where filaments intersect, the concentration of mass is so great that high-density nodes are able to form, containing hundreds or even thousands of galaxies. The cosmic web is real. We've mapped large swaths of it. Our galaxy is part of what's known as the local group, a collection of a few dozen neighboring galaxies near to our own. Our local group belongs to a larger collection called the Laniakea supercluster, which contains some 100,000 galaxies and measures 500 million light-years across. As you might have guessed, all these galaxies are strung along the cosmic web like beads on strings, perched along the edge of great voids. But even though we've been mapping this cosmic web for decades, most of what we can see is the beads, the distribution of galaxy clusters along the web, not the strings that hold them together or the filaments themselves. Or is it? Whilst most of the visible matter in the universe is tied up in galaxies, not all of it is. The dark matter in the cosmic web has a pretty strong pull itself. There, bound up as vast diffuse gas in those long strings or filaments, is where large-scale cosmological simulations have predicted we might not only find dark matter, but our missing visible matter too. This low-density, diffuse gas is known as the warm, hot intergalactic medium. But simulations are one thing, detecting these diffuse filaments is another. And this is where historically we've not had much luck, although that started to change about 20 years ago. In 2005, NASA's Chandra X-ray Observatory imaged two huge intergalactic clouds of diffuse gas. We'd seen clouds like this around our own galaxy and in others local to us, but not between distant galaxies. Could it be gas on the cosmic web? This was some of the first evidence that the cosmic web was hiding our missing mass, but the light was too faint to completely isolate it, so scientists couldn't quite be sure. Then, in 2012, a combination of 18 Hubble images was used to infer the presence of a filament funneling matter into the galaxy cluster MAX J0717. Scientists found it by studying the distortion of light from background galaxies due to the gravity of the filament's dark matter. But again, it wasn't a direct detection. We still couldn't say we've actually seen them. Inching ever closer to a discovery, it was just 2 years later that astronomers moved beyond indirect detection and statistical evidence into the realm of the visible. A team led by Sebastiano Cantalupo from the University of California observed an enormous filament of hydrogen gas. At nearly 2 million light-years across, they spotted it after it was illuminated by a giant cosmic flashlight, a bright quasar shining at it from 10 billion light-years away. This was the first time part of the cosmic web had been seen directly. Using the same illumination principle, in 2019, astronomers revealed whole networks of hydrogen filaments surrounding a massive protocluster, directly imaging the web on megaparsec scales. But these detections were only possible thanks to our cosmic flashlights. To understand cosmic filaments as they typically exist, in darkness, we needed a new imaging technique. And in 2023, scientists made a breakthrough. At the W.M. Keck Observatory in Hawaii, a team of astronomers had designed a dedicated instrument to search for filaments of hydrogen, more specifically, dim Lyman alpha emission, the spectral fingerprint of hydrogen as it absorbs and re-emits radiation. And it worked. In fact, they've made entire 3D maps of these filaments. This was just the start of the discoveries. In January 2025, the picture sharpened dramatically. A team of international astronomers captured one of the clearest direct images yet. Using the Multi-Unit Spectroscopic Explorer, or MUSE, mounted on the Very Large Telescope at the European Southern Observatory, they imaged a pair of quasar host galaxies with a cosmic filament about 3 million light years long. And using supercomputer models built on the MUSE data, researchers were able to simulate a filament that matches the one they observed in real life. This was a spectacular achievement. But there was a catch. These observations were from the early universe. They traced cooler hydrogen gas billions of years in the past, not hot, diffuse material thought to contain most of the universe's missing baryonic matter today. Our models predict it stretched along thin filaments of the cosmic web in the local universe, but here the signal is far fainter and harder to isolate. We were stuck. In June 2025, astronomers finally found what they were looking for. They were able to isolate and spectroscopically measure the hot, low-density gas of an individual cosmic web filament in the local universe, marking a breakthrough moment in our quest to locate the missing baryonic matter. A team of European researchers headed by lead author Konstantinos Migas at Leiden University in the Netherlands used JAXA's Suzaku X-ray Space Telescope to map a single filament in faint X-ray emissions over a wide area of space. They then used the XMM Newton to pinpoint sources of X-ray contamination, in this case supermassive black holes, which had to be removed from the data in order to map the filament. In this image, you can see what they found. A filament of the cosmic web connecting 4 galaxy clusters, 2 on each end, each one as a white spot surrounded by color. The band of purple stretched between them, resembling a honeycomb or bone marrow-like texture, is the filament of X-ray emitting hot gas. Located in the Shapley supercluster, a supercluster of more than 8,000 galaxies, the filament stretches across a distance of 23 million light years, which is the equivalent of about 230 Milky Ways end to end. Its mass comes in at roughly 10 times that of the entire Milky Way galaxy, and the temperature of the filament's hot gas is a scorching 10 million degrees Celsius. It reveals in detail for the first time how galaxy clusters are connected over colossal distances, and uncovers the vast cosmic web that underpins the structure of our entire universe, like the very bones of a cosmic skeleton upon which everything else forms. And according to the paper's co-author, the filament is exactly what we expected from the best large-scale cosmological simulations of the universe. We got it right. The latest breakthroughs in observing filaments lend important evidence and support for our current standard model of cosmic evolution, known as the Lambda cold dark matter model. The model is underpinned by dark matter, which has been too complicated for us to catch a glimpse of thus far, so observing this once thought missing visible matter on the cosmic web is a big step in the right direction. But to truly know whether our models match reality, we need more than 1 or 2 filaments. We need to map the entire skeleton, or at least much more of it. And that is where another mission, Euclid, comes in. Launched in 2023, ESA's Euclid mission is designed to piece together a more accurate picture of the cosmic web structure and history, and dig into the nature of dark matter and dark energy. Euclid will help us measure galactic shapes with precision, revealing how dark matter distorts space through gravitational lensing, and measure redshifts, giving us a 3D position for each galaxy. This combination will allow Euclid to infer the locations of the dark matter filaments, not just the galaxies on them, and give us precise locations to look for more gas. By 2030, Euclid will likely be able to confirm if the cosmic web matches results from the XMM Newton filament discovery, and the pattern seen in the cosmic microwave background. If it's a perfect match, that would be one of the strongest confirmations of the Big Bang model in the history of science. If not, then something is fundamentally missing in our standard model, whether it's our understanding of dark matter, gravity, or the early universe. Either way, with the help of Euclid and the latest observations of these cosmic filaments, cosmology is poised to be changed forever. Patreon members got access to this video ad-free, and more importantly, they keep Astrum grounded in a community passionate about space, not just YouTube AdSense and algorithms. So sign up with the link in the description. Being a member means you're part of the reason Astrum can focus on the kinds of videos people actually want to watch. It's where our most engaged viewers are, people who care about learning, exploring, and seeing what's out there. If that sounds like you, join the Astrum Patreon today and be part of where we're headed.